So good afternoon everyone and welcome to this lecture. This is a lecture in which we are supposed to do Ampere's law and we will go ahead with this. Before going, in the last class we had seen a few standard results. I had given those standard results so that you can keep them in your mind. The first one was a semi-infinite sheet at any point P like this, which is on one side of the sheet. Then we had discussed the formula for a infinite sheet with a fixed width, and the point is above the sheet. We had found the formula, then we had used this formula to find it for an infinite sheet. The formula is same as the formula for electric field due to an infinite sheet. Sigma by 2 epsilon naught was the formula, and here the formula was mu naught lambda by 2, and we had seen questions where we had used this. Yes or no? Also, for a hollow cylinder, we had found out the magnetic field. At the center, it is 0. Then we had done a question where we had a slit cut, and I gave you the formula for that. Then I also gave you the formula for infinite half cylinder. All these are standard results. Keep them with you. If a question comes, it would be a straightforward question. You just use the result and get the answer. Now, the next set will be the set on solenoid. What is a solenoid? A solenoid is nothing but it consists of a large number of loops, circular loops, which is wound around a non-conducting cylinder. The cylinder may be hollow, the cylinder may be solid, doesn't make any difference. That's a solenoid. So you have a cylinder and then you have wire wrapped around it. Everyone might have seen a solenoid. Yes or no? You've seen a solenoid?
Yes, sir.
You might have seen in the experiment where you make a electromagnet out of it. You have a core, then in that case it is a soft iron core, then you put a wire around it, you pass current, it becomes a magnet. That is nothing but a solenoid. Yes or no? Now this solenoid carries a current I, and small n is the number of turns per unit length, or I should say number of turns per meter of the solenoid. So small n is the number of turns per meter. So the total number of turns n will become n into L, where L is the length of the solenoid. Do we understand this? Yes or no? No or yes?
Yes, sir.
Sure.
For this solenoid, we can have a standard result, and the standard result looks like this. If I can make it here, I think I can post it here. So this is a solenoid, and if you want to find out the magnetic field inside a solenoid, you will not find this formula anywhere, so please note it. Inside solenoid, we have a point P. It's on the axis of the solenoid. Remember, it's on the axis of the solenoid, and the magnetic field. How do you find out the magnetic field? We can derive the result, but there is no time for us to derive it anymore. So what do? I join this point P to the two ends of the solenoid. Whether I join it to the upper end or the lower end doesn't matter. The angle is same. Then I make this axis, and I call this angle as theta 1, and I call this angle as theta 2. Remember, I is the current in the solenoid and the number of turns per unit length is n. If this is the case, if this is the case, if this is the case, the magnetic field at the point P of the solenoid is given by this legendary formula mu naught I by 2 sine of theta 1 plus sine of theta 2. Now this formula may remind you of something, and that is why I've drawn it in the same way. Does this formula remind you of something? Huh?
Finite wire, sir.
Finite wire, same formula, same thing. Now Talking about the direction of current, talking about the direction of magnetic field, you can see the current in the solenoid is moving like this, yes or no? So you curl your fingers around that, and you can see your thumb will point out in this direction, and that is the direction of magnetic field. Do we understand this? This is the direction of the magnetic field due to this solenoid that I have drawn. I hope we understand this. Yes or no? No, yes.
Yes, sir.
Huh? Note it down fast. I'll give you a minute to note it down. Well, this is actually the magnetic field due to a solenoid. You don't have to draw this. This is just for your understanding. This is how the current goes. Now, the direction of magnetic field, as you can see, is reverse here. Why it is reverse? Because the current is flowing like this. I. You can see a dot here. Dot here means current is coming out from here, out. And you can see a cross here. Cross means current is going in. So current is going like this. So you can see this is how the magnetic field lines of a solenoid is. This is how the magnetic field lines of a solenoid is. Remember, current is moving like this. We like this. So from top it is coming out and it is going into the lower phase. Do we understand this? And this is how the magnetic field of a solenoid look like. This is just for your understanding that this is it. Inside the solenoid, we can assume that the magnetic field is going to be constant. You can see the constant parallel line. Do you see this? Yes or no? No, yes. Huh?
Yes, sir.
Yes, sir or no, sir. So that is the magnetic field due to a solenoid. Now you have the result, and we can use that revolutionary result for different types of solenoid. For solenoid of infinite length, for solenoid of infinite length, some people call it ideal solenoid as well. For solenoid of infinite length, at any point inside the solenoid, what will be the magnetic field at any point inside the solenoid? And you can reuse that result and tell me the final answer. For infinite solenoid, which some people also call it as ideal solenoid, what is the magnetic field inside the solenoid? Yes, mu naught,
You are right.
mu naught into n into I. Do we understand this?
Yes, sir.
Point B at the end of solenoid, or you can call it semi-infinite solenoid. Semi-infinite. So the solenoid is infinite in one dimension, and it is finite in one dimension. If it is difficult for you to understand what I am saying, if it is difficult for you to understand what I am saying, here what we are trying to do in this case, what we are trying to do in this case is to find magnetic field at this point P, which is on the end of the solenoid. Do we understand this?
Yes, sir.
Magnetic field at this point B, P will be how much? Yes, you can put the values and give me the answer. That is also a question. What will be the magnetic field at the end of this? Huh? That will be equal to mu naught Ni by 2. One angle becomes 0 and the other angle becomes 90 degree. Do we understand this, or this has gone above our head saying bye bye?
Yes, sir.
Noted it down, sir.
Yes, sir.
Then there is this small thing. I don't think it can come, but you never know what can come in a JEE. Ideal solenoid, magnetic field remains constant anywhere inside mu naught Ni. At the end, it becomes mu naught Ni by 2. For a real solenoid, the diagram is like this. Noted it down, bacha? Eh?
Nothing, sir.
Okay, let me know once you are done. Well, then comes this small question, sir, and I hope that you can give me the answer for this one. A solenoid of length 0.4 meters and diameter 0.6 meter consists of a single layer of 1000 turns of fine wire, only one layer, carrying a current of 5 into 10 to the power minus 3 ampere. Find the magnetic field on the axis of the solenoid at the middle point and at the ends of the solenoid. You have 2 minutes to give me the answer for this one. So how are you supposed to do it? The first point is here, point P. I can join this end, I can join this end, I can join this end. Both the angles are going to be same. Yes or no? Yes?
Yes, sir.
Or no?
Yes, sir.
Let me call this angle as theta. I can find out the value of sine of theta. What will be the value of sine of theta? This side, the radius is given as 0.3 and this is given as 0.2. Yes or no?
Yes, sir.
So 0.3 square is 0.09 plus 0.2 ka square 0.04. So sine theta will become 0.2 divided by under root of 0.13. Yes or no? Yes or no?
Yes, sir.
So the magnetic field will be simply mu naught into Ni by 2 multiplied by 2 times sine theta. You can just put these values and get your answers. Remember here n is the number of turns per unit length. Here they have given the total length, total number of turns as 1000. So n will be equal to 1000, which is the total number of turns divided by 0.4. Do we understand what I've written here?
Yes, sir.
So no, you just put the values here and you will get the answer for this case. In the second case, what will happen is point P will go here. In this case, one angle is 0. You just have to find out one angle. This angle and this angle, I think, is very simple to find out. This distance is given as 0.3 and this distance is given as 0.4. So sine of this theta will be equal to 0.4 divided by 0.5. 4 by 5, yes or no?
Yes, sir.
So magnetic field here will be given by mu naught Ni by 2 multiplied by this sine theta, which is 4 by 5. So the answer in the first case is this. The answer in the second case is this. Do we understand this?
Sir.
Both the cases, you just had to find out the values of the two angles. One more small question. Everyone has understood this? Anyone got this answer? Have you noted it down? Then we have this question. This is a solenoid. The number of turns per unit length is N and the current is I. You have to find out the magnetic field at this point P of the solenoid. This is the question which is more likely to come, not the question which requires you a lot of calculation, but this is the form in which the question is more likely to come. So may I have the answer for this question, please? I'll give you 2 minutes to give me the answer. Mu naught and I1 plus root 3 by 4. That happens to be the correct answer. I just have to draw perpendicular. This angle would be 60 and this angle would be 30. Yes or no? Huh?
Yes, sir.
The magnetic field is simply mu naught n I by 2. Sine of 60 is root 3 by 2. Sine of 30 is 1 by 2. And this is your answer. If your current is like this, dot and cross, what will be the direction of magnetic field? The current is like this, dot, cross. I hope you understand. Yes. If the current is like this, what will be the direction of magnetic field? Right or left? Left or right? Top or down? In or out? Where? Huh? No one knows the answer. Huh? What will be the direction of magnetic field? Boys, girls, no one knows the answer.
Also, sir.
Huh? Current is coming out from here. Wee. Going down. Wee. So current is going like this. So what is the direction of magnetic field? Towards right, my dear friends. Do we understand this? Huh? Or it has gone above our head. Bye bye. Bye bye. Bye bye, sir. I'm going.
Understood, sir.
Oops. What has happened here? Hmm. Next one. Get me the answer fast, fast, fast. I don't have time. A straight long solenoid is produce a magnetic field B at the center. Straight long means it is infinite. It is cut into two equal parts and same number of turns are wound on one part in double layer. Same number of turns. Find the magnetic field produced by the new solenoid at the center. Simple question, sir. No answer, sir. The only formula that you have to use, sir, is B is equal to ideal or infinite or long solid mu naught Ni, where this N is nothing but number of turns per unit length. Now in the original solenoid, it is mu is equal to Ni. For the new solenoid, It becomes B dash.
L by
What happens to the number of turns? The total number of turns remains same, but the length becomes half. So the number of turns per unit length becomes how much? It will become 2n. Yes or
Yes,
no?
sir.
Huh?
Yes, sir. Yes, sir. Double.
Double, sir. So that is the answer, sir. Double, sir. Magnetic field will be double, sir. Nothing else, sir. What are you doing, sir? Do we understand this, sir? Or it has gone above our head saying bye bye, sir. Bye bye,
Understood,
sir.
sir.
I had a lot of lunch now. Girls, are you there? Or chilling out?
Chilling out.
Chilling out? Huh?
Sir, no, sir.
No, sir.
I don't get any voice from your side. Anyways, this is the next question, sir. I don't know, but I feel that magnetic field, the cylinder, the solenoid may come in this year in one of the sessions. A closely wound solenoid, 80 centimeter long, has a 5 layer of 400 windings each. The diameter of the solenoid is 1.8. You can assume it to be a long solenoid. Even though the values are not there, it should have been around 80 meter probably. But you can take it whenever question of solenoid comes, take it as an ideal solenoid. Do you understand this? Huh? Estimate the
Yes, sir.
magnetic unless and until that question comes where you have a diagram, only then you look at that formula that I had given. Otherwise, it is all that ideal solenoid. So you have this question. You have 2 minutes. Give me the answer. So basically, what you got to do? Be
4 pi to 10 to the power of minus 3.
correct.
At
Mu naught,
actual points.
mu naught Ni. You just have to find the number of turns per unit length. You have 5 layers of 200 turns, 400 turns each in each layer. So total number of turns is 2000. You just put the value, get the answer, and stay happy. So magnetic field on the first case is mu naught. The value of mu naught is 4 pi into 10 raised to the power minus 7. Total number of turns is 2000. Total length is 80 centimeters. So divided by 0.8 multiplied by 0.8. Yes, 0.8 multiplied by 8. That is the answer for the first case.
That is 2000, sir.
Huh?
That is 2000.
In the second case, B dash becomes mu naught n I by 2. That's the only difference. Do we understand this or this has gone above our head saying bye bye? Bye bye, sir. I'm going, sir.
Understood, sir.
Pakka, sir?
Yes, sir.
Girls, are we there or chilling out? Huh?
Understood.
Understood, sir. You understood is very dangerous. This one, my dear friends, is the next one. And we are done with that solenoid questions. I'll give you 2 minutes to give me the answer for this one. So how are we supposed to do this?
Same answer, sir. Calculation.
The length of the solenoid is 0.1. Diameter is very small. 2 layers. Remember, 2 layers. The wire is wound. First inner layer has 50, outer layer has 40. The strength of wiring in opposite directions. Both the current are same, but they are flowing in opposite directions. So, my dear friends, what will be the value of magnetic field? The value of magnetic field is mu naught n I. Now here there are two magnetic fields. So the net magnetic field B net will be mu naught n1 by L I minus mu naught n2 by L into I. Yes or no? Huh?
Sir.
Length is same, current is same, Current is in the opposite direction, number of turns is different. Yes or no? No or yes? Yes or no?
Yes, sir.
So we just need to put the value mu naught I by L into 50 minus 40, and that is the answer, my dear friends. You just need to put the value of I, L, and the answer that I have with me is 12 pi into 10 raised to the power minus 5 Tesla. Is it correct? Huh?
Yes, sir.
Yes, sir. Why did not you get the answer, sir?
Sir, we have done calculation. That one.
You
Pi.
have done calculation. Array, your power was not correct. You said 10 raised to the power minus 3. It is 10 raised to the power minus 5 that I am having. Calculation mistake cannot give us power mistakes. Huh? Can calculation mistake give me power mistakes? No, my dear friends. Anyways, I hope you have understood this. That finishes this part of our discussion, and we move on to the last part of this particular section of magnetic field, that is known as amperes. Ampere's circuital law. Ampere's circuital law. Now, before going on to Ampere's circuital law, let us rewind ourselves a bit. And I know that you don't remember things. The past छोड़ो कल की बातें, कल की बात पुरानी. नए दौर में लिखेंगे मिलकर नई कहानी हम हिंदुस्तानी. I understand that spirit, but let me ask you again. We had seen this first integral that came across was something like this. Does anyone recollect what was this?
Gauss law, sir.
Eh? You remember? Oh God. That is a big surprise, and I'm really surprised. Oh, it's great if you remember that it was Gauss law. So this gentleman was known as Gauss law. Did some times back. The surface integral of electric field over a closed surface, and what was it equal to?
Q by epsilon naught.
Ready? Q enclosed divided by epsilon naught. Absolutely correct. That was nothing but integral of this d phi, which is nothing but phi electric flux through a closed surface. I must have missed where the sun rose from today. I did not see it. I got up late. I should have seen it. Must have risen from the west. Anyways, comes the second thing. See, then we had done this. I have no idea. Integral of E dot dl over a closed loop. What was this equal to? See, sun definitely rose from the east, not from the west. Anyone recollects this?
Mu naught into I.
Electric field this is. Line integral of electric field.
Difference
over a
in,
huh?
difference in potential, sir.
This is, my dear friend, 0. This gentleman was Gauss law. This gentleman was change in potential in a closed loop is 0, which is nothing but change in internal energy is 0. Change in energy, conservative force, work done by this conservative force is 0. That, my dear friend, was your Kirchhoff's voltage law in a closed loop. Kirchhoff's voltage law. These are the two revolutionary laws that we saw in the previous chapter. In this chapter, let me take the counterparts. Counterpart number 1, integral of B dot ds. It will come in the next chapter actually. But let me introduce this gentleman here. Integral of B dot ds, surface integral of B dot ds over a closed surface. How much is that? Magnetic flux over a closed surface is always equal to 0. The magnetic flux over a closed surface will always be equal to 0. This is known as Gauss law for magnetism. Why it is 0? Why it is 0? Huh? Why it is 0? Just like that. How do I know, sir? It is 0 to 0, na. Let us move ahead in life. Why it is 0? Magnetic field is always in a closed loop.
Charge enclosed in the body is 0, sir.
And the pole enclosed in the body will be 0. If this is a magnet, bar magnet. Oh, this is a bar magnet. This is a bar magnet. Now, if I make a surface which does not have this magnet, there will be no pole, and therefore the flux will be 0. Do we understand this?
Yes, sir.
If I make a surface which has the entire magnet, it will have one north and one south. The flux is 0. Do we understand this?
Yes, sir.
If I try to enclose half of the magnet, even that half of the magnet has two poles, one north and one south, because north and south cannot exist in isolation. Magnetic monopoles do not exist. And therefore, the magnetic flux through a closed surface will always be equal to 0. Do we understand this? Huh? Magnetic flux through a closed surface is equal to 0. Then comes the fourth gentleman. What will be the fourth gentleman? Huh? What is the fourth gentleman? Line integral of magnetic field over a closed loop. Integral of B dot dl over a closed loop, and that is equal to
I enclosed. Epsilon naught. Epsilon naught into I enclosed, sir.
Take a deep breath. Deep breath. Then
No,
open
sir.
Yes?
Yes. Mu naught into I enclosed.
Mu naught into I enclosed. You can see this gentleman here in the denominator. This gentleman comes in the numerator. Everything happens. This law is known as what? Ampere's circuital law. Do we understand from where everything is coming? Huh?
Sir.
It is going above and it's saying bye bye.
Sir. No, sir.
There are only 3 fields that we have to study in the entire 12th standard and 11th standard. Magnetic field, electric field, and what is the third field? That we did in 11th standard. No, we did not do it. What is the third field?
Field.
Huh? Third field? Gravitational field that we experience every day. Gravitational field. So, this gentleman also exists for gravitational field. Surface integral of G. G is gravitational field dot ds. Can anyone tell me what is that equal to? Surface integral of gravitational field over a closed surface. I will not waste much time because I don't have it. Minus 4 pi into capital G into M enclosed. That this capital G is your universal gravitational constant. Everything is similar. This is known as Gauss law for gravitation. And the last but not the least, can anyone tell me what is the last but not the least? Huh? Line integral of G with dl will be equal to how much? This will be equal to 0. Because this is also a conservative field. Do we understand this or this has gone above our head saying bye bye sir? हो गया. Done. माफ कर दो.
Sir, understood.
Hello, I'll give you 2 minutes to show your talents, else I'll show mine. Okay, then we move ahead. And since the heading of the chapter, heading of this is Ampere circuital law. This is the statement of the Ampere circuital law. I hope you can understand the statement. And this is the diagram that is going to help us understand which current is positive and which current is negative. Integral of B dot dl is mu naught into I. If you are moving in the clockwise sense, ding 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 ding, if you are moving like this in the loop, then outward currents are positive and inward currents are negative. You only take those currents which are coming inside the loop and you don't take the currents which is going outside the loop. Do we understand this?
Yes, sir.
Same as Gauss law, the only thing is instead of taking surface integral, we are taking line integrals. The current that is coming in the integral, which will be only the current which is coming in the loop, and the current which is coming outside the loop will not be taken. It does not depend on the size or the shape of the loop. Any shape you make, this Ampere's law is always valid. Do we understand this?
Yes, sir.
Sir,
You have 2 minutes to show your talent, sir. In writing, sir. One more point you must understand and write. If the integral, we are saying that this integral, line integral is 0, that does not mean that the magnetic field is 0. The magnetic field exists, but the line integral of that magnetic field is 0. Do we understand this?
Yes, sir.
So the magnetic field is not 0, only the line integral is 0. That means the net current which is passing through this loop is 0. There is no net current which is passing through this loop. Let me know once you are done. Comes this simple legendary question. Find the values of integral of B dot dl for the loops L1, L2, L3 as shown in the figure. The sense of dl, so the direction is given. Depending on the direction, you have to tell me what is the integral of B dot dl, and I will give you a minute to think about it. What is the integral in this loop L1? Yes. Are we there, everyone, or chilling out? What is the integral in this loop L1? Loop is like this. One current is in the positive direction because the loop is like this. The one current will be in the negative direction. So it will be simply equal to mu naught into I1 minus I2. Do we understand this?
Yes, sir.
What's the then? Why is it not doing anything? Then comes the second loop, L2, green loop. Right? What the hell? Ah. Line integral of magnetic field in this loop. The sense of direction of loop is given. Dung 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 dung. I4 and I1 are positive and I2 is negative. So this becomes. Do we understand this or this is going above our heads? Why not the answer, sir? Then comes the third loop. There is nothing inside it. We get this or not? Huh? Do we get this or not? Yes or no? Everyone? Everyone is chilling out, it seems. We got the answer, beta. Uses of Ampere's law. Now, obviously, you can find out the line integral of B dot dl using Ampere's law. But obviously, that, as you can see, is not going to make some revolutionary questions. So, this Ampere's law can be used to find out the magnetic field. If you can create an Amperian loop, just like Gauss law, if you can create an Amperian loop, you can find it. You can find a current carrying wire which creates a uniform magnetic field, a field which is symmetric. You can find out the magnetic field due to that. We're not going to go into derivation. We are just going to write the first case is magnetic field B due to an infinite wire. It can only be used to find out magnetic field due to an infinite wire because this Amperian loop and magnetic field is only symmetric when it is infinite. We already know the magnetic field due to an infinite wire. It is mu naught I by 2 pi r. Yes or no?
Yes, sir.
We can now find it out in this way. In the first case, when we found it out, we drew the diagram like this. Wire was like this and the point was here. Now we draw the diagram in a different way like this. So the current is coming out and the point is here, and you can see that the magnetic field is going to move in a closed loop. Yes or no?
Yes, sir.
We have to find out the magnetic field at a distance r, and you can assume, you can understand that by the symmetry of the figure, the magnetic field is going to move in a circular path. Yes or no?
Yes, sir.
At all the points on this circular path, the magnetic field is going to be same. Yes or no?
Yes, sir.
We can now find out the integral of B dot dl. The integral of B dot dl. In this particular case, the integral of B dot dl, B and dl are in the same direction. Yes or no?
Yes, sir.
Magnetic field is also in this direction, and also I'm looping in the same direction. So B dot dl ka integral simply becomes B into 2 pi r. Yes or no?
Yes, sir.
And that becomes equal to mu naught into current enclosed is I. So you can find out the magnetic field due to a straight long infinite wire will be mu naught I by 2 pi r using the concept of Ampere's circuital law. Bye bye. Bye bye. Bye bye.
Understood, sir.
Everyone has noted this down?
Done, sir.
Done, sir. Shall I move ahead in life, sir?
1 minute, sir.
1 minute, sir. Okay, sir. Take your 1 minute, sir.
Done, sir.
Well done, sir. The next one in the line that comes is magnetic field due to an infinite hollow cylinder. And we have done one part of this where we found out the magnetic field due to an infinite hollow cylinder inside the cylinder. Yes or no? And I told you that the inside field is zero because there is no current and everything is cancelling each other out. Yes or no?
Yes, sir.
So magnetic field inside at any point will be how much? It will be 0. Do we understand this?
Yes, sir.
For any point outside, remember the radius of this. The radius of this is capital R and the point is outside at a distance R. If you now create this Amperian loop, you will get the magnetic field outside as mu naught I by 2 pi R. It is exactly same as the magnetic field due to an infinite wire. Do we understand this?
Yes, sir.
So this hollow cylinder only behaves as a infinite wire. For any point outside, the magnetic field is going to come as same. Oops. Do we understand this, or this has gone above our head saying bye bye sir, I'm going sir, bye bye sir, I'm going sir, bye bye sir, I'm going sir. This, my dear friends, is the graph of magnetic field of a hollow cylinder as a function of R. As you can see, inside the cylinder, the magnetic field is 0 and outside it keeps on decreasing. Does this graph remind you of something that you have already done in the previous chapter? This graph is exactly similar to the graph of electric field
Due to hollow space, sir.
hollow sphere or a conducting sphere. Inside it is 0 and outside it is going. Here it is inversely proportional to R. There it was directly inversely proportional to R square. Similar things. This is also the same graph as the graph of electric field due to an infinite hollow cylinder. Similar thing will come there. Do we understand this?
Yes, sir.
It has gone above our head saying bye bye.
Understood, sir.
Remember, all these cylinders are infinite. Shall we move ahead in life?
Yes, sir.
The next one that comes into the picture is solid infinite cylinder. A cylinder is always solid. Just writing it because everyone says solid cylinder. So the cylinder is now solid. It is like this. The cylinder is now solid, so it has material inside it. So current is distributed along the area and current density is given by I by pi r square. Do you understand this? So the current is distributed throughout the area, throughout the cross section area. Do you understand this? Yes or no? No or yes? Do you understand this, bacha? Now, I ask you a simple question. Will the magnetic field inside the cylinder be zero now? Now, inside the cylinder, the magnetic field is not going to be zero. Yes or no? Because this loop, this pink loop that I am going to create inside the cylinder will also carry some current. Yes or no? No, yes. Yes or no? No, yes.
Yes, sir.
Magnetic field inside this cylinder is given by this formula. Remember this, mu naught I into R divided by 2 pi capital R square. That means this magnetic field is directly proportional to R. This will again remind you of that solid non-conducting cylinder, solid non-conducting sphere. Does it remind you? Magnetic field at any point outside will remain same. It will be equal to mu naught I by 2 pi R. Do we understand this, or this is going above our head saying bye bye sir, bye sir,
Understood, sir.
bye bye sir?
Understood, sir.
And this is how the graph looks like. And where is the magnetic field maximum? The magnetic field is maximum on the surface. Do you see this same diagram which we draw? Solid cylinder, solid non-conducting sphere. B on the surface is maximum. Mu naught I by 2 pi capital R. This B is inversely proportional to R. Do we understand this? Yes or no?
Yes, sir.
Everyone has got this?
Yes.
Okay. Shall I move ahead in life?
Yes, sir.
1 minute, sir.
Yes, bacha?
1 minute.
Yes, sir.
1 minute, sir.
Okay, sir. You have 1 minute, sir. Let me know once you are done, sir. Done, sir. I will have to wind out this class at this point in, sir, because there are some cases still remaining. We will be covering those cases in the next class, and hopefully we would be able to wind up this chapter in the next class, because there are questions that we need to do. There are some questions that we need to do so that this concept becomes clear. So we will wind this up in the next class, that is tomorrow. I'll also try to take some questions from your previous year based on what we have done till now, and we'll probably start with the next one, which is magnetic force. Only two things are left now: magnetic force, 2 or 3 classes it should take. EMI, that will take some 4 or 5 classes, and then AC. We are done with your electromagnetism, and I hope that I can do it uh, as soon as possible, whenever it is possible to do it. Okay, so I'll see you in the next class tomorrow. And before coming to the class, please go through all this formula. I have already sent you the sheet for this. Yes or no?
Yes, sir. Yes, sir.
If you
Yes, sir.
just do even 30% of that sheet, 30% I mean not from 1 to 30 questions, 30% of each section. If you can do 30% of each section, even some of that question will be coming in your exam. So just do that at around 200 questions in that sheet. I think we would have covered somewhere around 100 questions up till now. By the topic that we have covered, only more than half we have covered. Only magnetic force is remaining, which should be over in 2 classes if everything goes fine. So by the end of the week, I am hoping that we can cover your EMI complete. I'm hoping that we can do EMI, and then the next week, starting of next week, AC, and then in the 4 or 5 days, semiconductors. So by 20th of this month, you should be done with your course. That's what I'm hoping for. Anyways, please keep doing the exercise that I have sent. Take it as a revision class. It's good that we are doing it for the first time now, because the majority of the portion that we are doing now is going to come in your exam, and this is very, very fresh in your mind. And I've covered absolutely everything that is possible in this universe to cover. I'm very confident not even 1% question can come out of what we have taught or I have taught. Same question will come. I can assure you that. And I'll show it to you. Once I get the paper, I'll show it to you. Take care and God bless all of you. Bye bye. I'll see you tomorrow. Don't be late. Time is a luxury that we don't have. Bye.